Here we are on Tuesday, the last day of regular potential energy discussion, and we're going to talk about springs and a spring energy example. So I have a really simple example set up involving a block and a spring, and we're going to try to dissect this and figure out everything we can about this. There we go. So we're going to have a vertical spring. I'm going to draw the ground here, and I'll draw the spring here like that. And we're going to take this spring and place a block on top of it. And when you place a block on the spring, it's going to squish the spring. So we're going to have a level here and a level here. And that distance there, that's my 7 centimeters. And why is it compressed? Because we put this block on top of it. So that's stage one, the first sentence. And I can use that to figure out some things here. Here is my 2 kilogram mass, and it experiences the force of gravity, which is 2 times 9.8 equals 19.6 newtons. And it experiences an upward force, F sub s. And when we say that this block is placed, causing it to compress, what we mean is that this situation is at rest. So that means that this force of the spring and the force of the gravity must be equal to each other. Newton's second law would be force spring minus force gravity is equal to 0 because we're at rest, no acceleration. So we end up with force spring equals force of gravity equals 19.6 newtons. And that allows us to learn something really important about the spring. The way springs work is the magnitude of their force is proportional to the magnitude of their stretch or squish. So in this case, it means that 19.6 newtons, which is the spring force in this situation, is equal to some constant K times the amount of compression of the spring, which is 0.07 meters, which tells me that K for this particular spring is 280 newtons per meter. And that is called the spring constant, or the stiffness of the spring. Some people call it the strength of the spring. I don't like that term because in engineering, the strength of a material can mean lots of different things, and there's an entire course talking about different ways we talk about the strength of materials. So I'm willing to call it the stiffness of the spring, but I like calling it the spring constant. So that's pretty much what we get out of situation one. The first sentence is we learn what kind of a spring we have. In physics 2, we do a laboratory with springs where we hang a block from a spring and then pull it down and let it go bouncy, bouncy, bouncy up and down and measure that. And this is one of the big topics of that laboratory is how much of a spring constant do we have? Now, what happens when the block is pressed 11 centimeters further? So now we're going to have a kind of a third diagram. Let me grab these things here and paste that and get rid of some stuff up here. Whoops, that one. So now in my third diagram, we're going to take this spring and really squish it. So it's here. So this is 11 centimeters. And here's the block. And in order to do this, we're going to have to put a hand here. So there is my impression of somebody putting a hand or a foot on there. I don't know what I drew. It's terrible, really. So let's think about our 2 kilogram mass now. It's going to have the downward force of gravity, which is still 19.6 newtons. It's going to have the upward force of the spring, which is K times the X of the spring. And it's going to have a downward force applied. It's a normal force from the person's hand. Just call it force applied. And what do you know? Calculate this force of the spring here. This is 280 newtons per meter. 0.18 meters. Because the X of the spring, the amount of compression or squish of the spring, is the original 7 centimeters plus 11 centimeters is equal to 18 centimeters. So I put that in as 0.18 meters, and I have to calculate some things here, and the new X of the spring is K times that's supposed to be a plus. There we go. So this comes out to 50.4 newtons. So now, when we look at our Newton's second law equation, it would be force of the spring minus force of gravity minus force applied. I guess it makes more sense to make the minus signs the color of the symbol that's there. Equals 0. So we know how strong the spring is. That's 50.4 newtons. We know how strong gravity is. That's minus 19.6 newtons. And then we have minus the applied force, which we don't know is equal to 0. So that's what tells us that the force applied is equal to 50.4 minus 19.6, which is I think 30.8. Yeah, I shouldn't try to do math in my head. That's bad. So our conclusion so far is that it would take an extra 30.8 newtons to cause the additional compression of the spring. So now, what happens when we let go? So that applied force isn't there anymore. So now the forces are no longer balanced. So we get our diagram for the block is force gravity equals 19.6, and the force of the spring equals 50.4, and our Newton's second law equation is force spring force gravity equals acceleration. So we already know what happens when we plug these numbers in and subtract them. We get 30.8 on the left side. Our mass is 2.0 and acceleration. So we get A equals 15.6 meters per second squared. So the block will start rising at 15 meters per second squared of acceleration. Now, we could possibly maybe figure out how high it goes using the idea of acceleration, but this is difficult. The big problem is that springs provide a force that depends on how much you compress them. And that means that as this block starts to rise, the spring force is going to get smaller and smaller and smaller. The force keeps changing. That means the acceleration keeps changing. And we don't have the math for that. So we're going to use spring energy. And the way spring energy works is the potential energy of a spring is 1/2 K times x of the spring squared. And I went through this in the notes from last year. So if you really want to see why this is true and why there's a little factor of 1/2 in there, you can definitely go see that. It's also in the textbook, very thoroughly described in the textbook. We're just going to use this now. So now we'll do an energy analysis. And we'll still have these 3 diagrams. So we'll have, actually, we're going to have 2 diagrams that are important to us. We're going to have this one. I'm going to grab that. And let's move that up here. There we go. And then we're going to have this one. Copy that to the clipboard and paste it here. And we'll move that here. I think we'll move that up too high. Okay. And then we're going to get rid of our hand here because we're letting go. There we go. And we have this level here and this level here. And I'm going to draw the block right there. So these states are initial, and I'm going to call this condition 2, which is when the spring releases the block. And then I want one more where we have this and the block goes up here somewhere. And I'm going to call this condition 3. So this is condition 1 and max height. So our basic idea of conservation of energy is we're going to try to do initial plus work equals. We need to figure out how much energy we have initially, and then figure out whether work is a thing that we have to include in our energy analysis. And then we have to figure out how much energy we have at the end and how it's related to things we want to know. So this is 18 centimeters, and this I'm going to call H. So forms of energy we care about are kinetic, we care about spring, call that E. Spring is 1/2 K spring squared. And we're about gravity. Think of gravity a different color. I'll call it PE. Gravity is equal to mgy. So we need to figure out these 3 types of energy. And as it turns out, in this particular analysis, we don't care about work because all of the forces involved are already included in the analysis. We have gravity that's included by potential energy due to gravity, and we have the spring force, which is included by the potential energy due to the spring. If there was another important force, if there was like friction, like the example I did yesterday, then we would have to have work due to that additional force. We don't need that. So in state 1, our energy is equal to K plus U of the spring. I'm sorry, we don't call it U in this class. We call it PE of the spring, and then plus PE of gravity equals. So in condition 1, when we first release the block, there's no kinetic energy. It hasn't started moving yet. There is 1/2 times 280 times 0.18 quantity squared of potential energy. So 1/2 times K times that X spring squared. So this will be 0 plus 4.536 And then we're going to have plus 2, 9.8. And then we need to pick a 0 for y values. Because I mark this height here as above this point here, I'm going to set y equals 0 right here in the middle. And it turns out that that's easier for the question you have in your homework that involves vertical motion and a spring. So if you do that when you're doing your homework question, it'll make the homework a little easier. Minus 0.8. So this has a negative gravitational energy of PE gravity mass 2 times 9.8 times the distance. Negative 3.528. 3.528. So we have that plus that is 1.008 joules. So that's my initial energy in my balance of energy thinking. In state 2, when this block gets to the top of the spring, the moment the spring releases the block and the block starts flying, we're again going to have K plus PE of the spring plus PE of gravity. And this is going to be K is 1/2 m squared. Because we don't know how fast it's going, so we can't just calculate K from that formula. But let's see what else we got. Potential energy of the spring, that's going to be 0 because that's where the spring naturally would be. That's the spring will release the block when its force goes to 0, and its force goes to 0 when its x goes to 0. And when you put x equals 0 into the potential energy of a spring formula, the spring potential energy is 0. And then we also get a plus 0 for gravity because I set y is equal to 0 at that point there at point 2. And what this is 0.08. This is the idea that the initial energy equals the final energy. So we can take the value we got for the initial energy and set it equal to the formula we got for the final energy. Now we can solve for V. So we get 2 times 1.008 divided by the mass. The mass was 2 kilograms. And that would be V squared. I want regular V. So we end up with that. So K equals 1/2 mv squared becomes V equals the square root of 2K over M. You want to practice that until you're good at it because you don't want a little algebra thing to be the reason that you're making mistakes. So now I can calculate this V in condition 2, square root of 2 times that kinetic energy over the mass value equals 1.004 meters per second. So compressing the spring by 18 centimeters, including both the spring energy and the gravitational energy, is equivalent to setting up a launcher that can launch our block at about 1 meter per second. So now let's look at state 3. And this will about wrap it up. Energy is equal to, in state 3, we're going to have K energy. And in state 3, the spring is no longer an issue. We can skip the spring. Basically, the spring energy got to 0, and it's not going to do anything else against us. So now we have our kinetic energy is 0 at the very tippy top of the motion, because when something goes up into the air straight up and comes back down, it has to briefly stop at the very top. And then we get our plus potential energy due to gravity is mgh. It's mgy, and our y value is called h here, so I can call it mgh. And that is equal to 1.008 joules. The same amount of energy we started with is the same amount of energy we had in the middle, is the same amount of energy we had at the end. So now we get h is equal to 1.008 joules to 5.8 newtons per kilogram equals that amount of energy over parentheses mass times 9.8, 0.051 meters equals 5.1 centimeters. So, what do we do with our energy balance? Compressing the spring gave the spring that 4.536 joules of energy. That energy was allowed to be released by letting the spring relax, 3.528 joules. And out of that 4.536 joules, there were 3.528 joules were just used to raise the block, and 1.008 joules were left as kinetic energy of the block. And that 1.008 joules of kinetic energy were converted to gravitational energy here at the end in state 3 as the block rose to its final height. So there's an example that involves an interaction between spring energy and potential energy due to gravity. So hopefully that can give you a lot of insight into how to do conservation of energy analysis.